going out with the flying clusters, flying species. So there is some space charge which is developing. And if too much of space charge develops, even if you are pumping in energy, plume formation stops because ions are not able to move out. They are called back to the target, right? So these are the experimental difficulties. In order to avoid that, what one does is simply rotate the target material as shown here. Well, you have to do it from outside of the vacuum, okay? Carefully. And then you are essentially exposing the laser every time. These are pulse lasers typically, to every time to a fresh area on the target. And after a minute or two, probably the same area gets exposed, you don't mind. So you end up cutting a spiral groove on the target and again come back and revisit that area, it doesn't matter. But you can't be sitting on the same area. The plume volume will decrease in no time. These are the experimental difficulties. Now, this is how a typical setup would be. You have a vacuum, you need to have vacuum if you want to control the composition, right? And it's connected to vacuum pumps. You have the laser coming from outside through an optical window getting focused here. As I said, you need a rotary motion to the target. And what else is important? You want to create a given gas atmosphere, you can do that. You can also heat the substrate. Sometimes you heat the substrate so that the species which are coming in to deposit, they get annealed as they get deposited, right? You will have an annealed film which perhaps helps in terms of the electron transport in devices. So all these facilities would be there around for laser ablation setup. This is how a typical plume looks like. You can see here, this is the target and there's a lot of white light coming out of that because laser has just hit. These are typically few nanosecond lasers and you see the plume coming out. And that also will be around only for probably, visually you see it for a millisecond or so and then it dies off. Next pulse comes. These are repetitive pulses, so you don't really make out, you see almost a constant plume being around there. And what do you do with the plume? I told you that you can make a 2D film, fair enough, but if you want to make some clusters, you want to make something else, how do you go about it? There are many methods. Having done the laser ablation, there are many methods for aggregation. Simple gas aggregation, which also can be done without the laser by other means as well, as I've shown there, is that filling in helium and let it cause some aggregation of species and then they will grow as particles and whatnot. More interesting one, which gives really atomic precision, is the supersonic jet. Here is a supersonic jet system. This is also called after the inventor, Smalley's technique. And what is done here is, this technique effectively utilizes the Joule-Thomson effect. So you are pressurizing helium behind the vacuum chamber and through a very narrow orifice, you are pushing the helium in pulses. So 10 atmosphere, helium gets in a small pulse into vacuum. So what will happen? Suddenly the free expansion of helium takes place and then helium is cooled to few Kelvin from room temperature. So you're essentially producing a cooling agent inside the vacuum in pulses. Okay? You don't want to create too much of atmosphere of helium, it will cause other growth issues. So you want to maintain vacuum. And as you're pumping in these helium pulses, laser is coming from the other direction and ablating this material. So you have built a cell around here wherein the plume which is produced is being hit from the other side with this cold helium pulse, right? The whole thing is carried away at supersonic velocity, typically 1.5 times the velocity of sound, like this. And as it is being carried, we can see that in the flow itself, many things happen. Because a hot vaporized material from that whatever your target is, it is getting intermixed with cold helium. A lot of nucleation takes place, right? Fullerenes and other species. This is what exactly they did. Smalley and Croto joined by James Heath. So as these clusters fly out, you will have to control it actually. So you have to be working with the beam dynamics. It's no longer a simple jet, it is supersonic jet. So you have to have the right kind of beam optics there. This is a material optics. And then steer the beam, take it in a direction you want, and then you play with what you want. okay, in terms of just put a substrate and collect a couple of clusters and analyze, or you can go further to do other things. There are many variations possible, and all these have been explored in the last 2 decades. Books have been written on this actually, right? As you do this, you can bring in another beam from another direction and cause beam collision, one cluster beam, another cluster beam, beam collision, and what kind of species come up. These kind of very academic studies have been carried out by people, and we have no time to get into those details. I just wanted you to be aware of the fact that there have been such sophisticated measurements, studies in the literature. Here is the setup, typical setup. We built it in the lab, by the way. So here you have the molecular pulse valve, which is injecting the helium pulse into vacuum, and you have the laser coming in, the target being rotated. These are all the beam optics part, and it enters into another zone where you're ionizing the species. Small clusters are being ionized, and then here these are actually taken away into the time of flight tube. You're measuring the mass of them. Okay, so your mass characterizing the cluster. That is simply the first thing one would do whenever one is working with beam, cluster beam. And having done that, mass spectrometry, you will know what kind of species are there in the beam, right? That's the first thing to know. And having learnt about it, you want to apply perhaps a mass window. That means now since the beam is timed, you will have a perfect control on which cluster is walking across at a given point of time, because they are flowing in the mass tube, time of flight tube. So you can put a mass window, a chopper, and you can select at a given time, I want only C60, C60, nothing else. So every time a repetitive pulse is coming, you are allowing nothing except that particular mass. So you can collect it on a substrate, or you can pass through a solution, do many things. So this is what people do. During the flight, they measure the reactivity, magnetic moment, and also carry out collision studies. And in terms of soft landing, taking the clusters, making them land on a given substrate, softly land them, otherwise you will destroy their structure. How you softly land them? You coat the substrate at cold temperatures with a bed of argon, and then make these clusters impinge on the substrate. What will happen? All the energy is transferred to argon bed. Argon will evaporate, so you will have the clusters landing safely without fragmentation, right? Because they are coming at supersonic velocities. And you carry out electronic structure, spectroscopy, reactivity, magnetic nanostructure, and whatnot. So ample studies are there in the literature related to all these aspects. I am having good number of results collected with me, and if anyone is particularly interested, see me after the talk. I'll pass on all that wealth of information to you. There's also another possibility. You can just make it pass through a solution, a solvent, where some molecules are waiting to capture the clusters, get them ligated, and form a dispersion. Such possibilities also exist. Let us look at one mass spectrum. If you take simple graphite, you're able to see? Barely. You are able to see it there? Okay, fine. So if you take a chunk of graphite and hold it as a target in the system what I just explained, you will have the carbon clusters walking out of your entrainment region. And if you do mass spectrum of them, you'll get to see, for example, monomer carbon, dimer, trimer, it goes on, you see. And then you start making cage molecules now. You are here, C20, right? Look at C40, C44, C60 is here. And then C70, C82. Each one is representing, each peak is representing mass of a given cluster, right? So the beam coming out is having all mix of different clusters. This is where probably you need a time window, mass window, so that you can select the cluster you want. When you are able to define clusters with such mass precision using this time of flight tube with a mass window, you'll be able to select those clusters, right? Say 59 I can select, say 60 also I can select separately. I can carry out studies. So many such studies have been done using a combination of laser assisted ablation, Smalley's entrainment cell, associated beam dynamics, time of flight mass tube, plus a mass window. Look at that sophistication required. With all that together, you'll be able to do very meaningful studies which will clearly address the intrinsic properties of such small clusters. We'll now change the gear and go to chemical methods. Whatever I said so far has given you a flavor of what are the physical methods around. Yes? So we will now move to chemical methods. In chemical methods, it's much more a richer word, at the same time also perhaps to some at least quite confusing. You see here, the produced nanomaterials, what we typically call nanoparticle, people tend to use the name cluster, nanocrystal, colloid, nanoparticle, so on. I have listed out here just to remove, bring in more clarity with respect to terminology. You can see that. Everything is tiny. Can we use these words interchangeably? It becomes very important when you are dealing with the nanoparticle system. You tend to call something as a cluster when you know the nuclearity, right? C60, C70. And you tend to call something as a nanocrystal when you know the lattice. A colloid is something, same system, nanocrystal only, but you tend to call it as a colloid because you have dispersed it in a given solvent. Then nanoparticle is a very generic word. Physicists tend to use the word nanoparticle more often than chemists. Chemical methods. This is the picture, image of the sol what Michael Faraday prepared. Well, same technique was used to prepare these particles. What do you get to see? These are gold particles in a transmission electron microscope as seen through TEM. And you have these particles which are around 10 and 15 nanometer in size, in diameter, more or less spherical, but some odd shapes are there. A lot of the particles carry these striations. There is a lot of twinning happening there. These are called multiply twin particles. They are not single domain particles. Right? All of them are Brownian particles. They are easily dispersible in solvent, and they come in various shapes and sizes. So what do you do with them? If Michael Faraday prepared 1.5 centuries ago, what do we do with them? I told you in the morning, redispersibility of the particles is one very important aspect. And now I'm coming to size and shape control. How do we control? This Faraday's sol has all sorts of shapes and sizes. Well, it was one first step crude method, right? So how do you now bring in finer control with respect to the particle size and the shape? And of course concentration, which is even more difficult to address. And as you do, you will realize that you need the help of some molecules to ligate them, to stabilize them. So we'll go through a couple of examples and learn how this is being practiced in the literature. One way of doing it is to prepare particles and ligate them and stabilize them. The other way, even cleverer way, would be actually nucleate these clusters in solution while you have the organic ligands ready to capture them, or your starting material itself may contain the ligands, as I gave the example of AU55. For AU55, you would start with, you will have the triphenyl phosphine around, you will have the gold chloride around, a mild reducing agent around, whole thing is refluxed. So everything is around there. You are not going to do a second step of adding something to stabilize it. And as you grow, you may end up with these magic nuclearity clusters which we talked about in the morning. And these facets get decorated with ligands, and that's how they get stabilized. This is a popular technique to make well-defined clusters. It had been a technique with very low throughput, but in the last 5 years there have been paradigm shifts in the way one would do the synthesis of this, and nowadays at least a gram quantity of these small tiny particle systems are being made, and also some of them are commercially available. These are magic nuclearity clusters. Even simpler method is shown here. For example, this one is containing a PD system. Each PD is now a cluster with 561 atoms, and that is prepared with rather a simple method, taking H2PDCl4 and reducing it in ethanol water mixture of a given concentration. While you need something else here, that is PVP, polyvinyl pyrrolidone. PVP many times is used to cap metals, mostly metals, and it is not a direction guiding agent. If you want simply a coat, neutral coat on a metal particle, use PVP. And it is not affecting the growth, it is only controlling the rate at which the growth takes place. The shape is not directed by PVP. And as the particles grow, the right kind of concentrations will judge to what maximum size the clusters go. Importantly, all of them grow uniformly. So you will have now a collection of PD particles wherein each one is 2.5 nanometer wide, containing a nuclearity of 561. So a lot can be played around with this kind of what are called polyol synthesis methods. I have classified here different methods. Brushed method, which I am going to deal with in a little while. Polyol, I already showed an example. There are a lot of interface methods involving air, water, and liquid-liquid interface methods. Perhaps we'll have one or two results from this. And then there are combustion and catalytic preparations. I may not have time to get into these details. Do realize one thing: it is much easier to prepare noble and semi-noble nanomaterials, nanoparticles, than reactive 3D metals. Okay, it's much